Question 1. The left-hand rule can be used to identify the direction of the force acting on a current-carrying conductor in a magnetic field. And then we've got a diagram of Fleming's left-hand rule, and all we've got to do is say what each digit represents in Fleming's left-hand rule. So we have the forefinger. So your forefinger represents the field. We have second finger. So second finger represents the direction of the current. And finally, we have the thumb, which represents movement of the wire. But there's a problem, which is movement isn't an option here. So actually, what we need to write is it's the force that acts on the wire, causing it to move. So we've got forefinger field, second finger current, and thumb, which is movement. But on this diagram, we need to use the word force, which causes the movement. It's a pretty straightforward question to start. The only difficult bit is we often think of the digits in a particular order. So I've often spoke about thumb for movement, forefinger field, second finger current, and you can see these are written in a different order. So you have to be a little bit careful about forefinger, second finger, movement or force. Okay, moving on through the question. We're then given a figure 2, which shows an electric motor. So you can see we've got a circuit set up. The current is flowing in this direction. They've helpfully given you arrows. If they don't give you arrows, you should know that the current always flows from the positive terminal to the negative one. So the long part of the cell is the positive terminal, the short one is negative. So we're going from positive to negative. Draw an arrow on figure 2 to show the direction of the force acting on the wire AB. So now we've got to use Fleming's left-hand rule. So we take our left hand, we are going to point our forefinger in the direction of the magnetic field. So that's coming across the page. The current is going off into the page. So I need to turn my hand around so that my second finger is pointing the same direction as that wire there. So we're going to flip my hand round like that. And you can see my thumb is now pointing downwards. So I've got forefinger matching up with the field, second finger matching up with the current. My thumb is pointing downwards. So we would draw an arrow on the line AB, pointing vertically downwards. Suggest 2 changes that would increase the force acting on the wire AB. Well, you could have increase the current, it's not acceptable to just write current. They've said 2 changes that would increase the force. So we have to say we would increase the current. We could increase magnetic field. So increasing the magnetic field strength of the permanent magnet. And actually you could, if you remember F equals Bill, we could increase the length of wire that is within that magnetic field. But actually I think these 2 are the 2 to go for. Increase current or increase magnetic field strength. Over the page, suggest 2 changes that would reverse the direction of the force acting on the wire AB. So actually this is very similar to those little supermagnet motors that you made. You could either reverse the current, and with those supermagnets we did that by changing the cell around, or you could reverse the magnetic field. So let's say reverse the poles of the magnet, so that the magnetic field is flowing in the opposite direction. Okay, on to the last part of the question, which to be honest isn't really about magnets, it's about efficiency. So a student uses an electric motor. So there's your tenuous link to magnets to lift a mass. This is shown in figure 3. The student varied the electrical input power to the motor. For each different electrical input power, he recorded the time taken to lift the mass, then calculated the output power. Fine. None of that really matters because actually what you've got to do is calculate the efficiency of the motor. So efficiency is equal to the output. So remember it's test D. So test D, the output is 120. So I'm doing the output divided by the input power. So again, test D, my input power is 80. So I've got 120 divided by 80, which comes to 1.5 or 150%. 150% if we then times the answer by 100. We're told that this is anomalous. So this should be a surprise. You can't have an efficiency of more than 100. And we're told that it's anomalous. So over the page, we've got suggest a reason. Oh, actually, it's not photocopied, has it? It says comment on this. So what it's expecting you to say is that the efficiency is greater than 100%. Now that's impossible. Humans have not invented anything that's even 100% efficient, let alone greater than 100%. So this is impossible. So our comment, the surprising thing about this is that the efficiency is greater than 100%. The reason, well, it's going to be to do with the timing. Actually, particularly if you look at the pattern here, 2.4, 1.2, 0.8, it seems to be going down by 0.4 each time, and then it goes down by 0.6. So we would suggest that the recorded time is too short. They've made some sort of error with the stop clock. Again, that last bit, it's not really about magnets, is it? But it's a how science works question. So you should try and remember that you never get an efficiency of more than 100% or 100% or more. So this is impossible. They've told you it's anomalous, and they want you to say, well, the weird thing is the efficiency is greater than 100%, and then suggesting a reason for that. On to number 2. And actually, as you work through these, you're going to start to notice similarities between the questions, because there's only a limited amount of stuff they can ask about this topic. So again, we've got a diagram. The diagram shows a demonstration carried out by a teacher. When the switch is closed, there is a current of 2 amps through the wire. So here we've got the wire, and here's our switch. The wire experiences a force and moves. Kicking wire experiment again. Use the correct word from the box to complete the sentence. This demonstration shows the. So wherever we are generating some sort of movement, we call that the motor effect. So the kicking wire is the motor effect. Those little spinning super magnet motors we made, that's the motor effect. So when we're using electricity in a magnet to make movement, we have the motor effect. And then this is what I'm talking about with regards to similarities. State 2 changes the teacher could make to the demonstration, each of which would increase the force on the wire. The teacher does not touch the wire. So just like before, what could we do? Well, we could increase the current. And this is important. You've got to use the word increase. They've said you want to increase the force. You can't just write current. You have to say increase the current. And we could increase the magnetic flux density. Not a word to be misspelled. Of the permanent magnet. You should definitely specify we're talking about the permanent magnet. Or you could increase the length of wire that is inside the magnetic field. So you see, this is really similar to that question that we had in number 1. Suggest 2 changes to increase the force, or increase the current, increase the magnetic flux density, or increase the length of wire inside the magnetic fields. Over the page. So, state one change that the teacher could make to the demonstration to change the direction of the force on the wire. Alright, so, easiest one. And actually it was in the video that we watched the kicking wire. We could reverse the current. They could also reverse the direction of the magnetic field, so turn the magnet around. With the switch closed, the teacher changes the position of the wire so that the force on the wire is 0. So with the switch closed, the teacher changes the position of the wire so that the force on the wire is 0. So, what must the position of the wire be? 90 degrees to the direction of the magnetic field? Well, do you know what? That can't be right. Because if you look, it's already at 90 degrees. We know there's a force when we've got the wire at 90 degrees to the magnetic field. 45 degrees to the direction of the magnetic field, or parallel to the direction of the magnetic field. And the correct answer is that last one there. If the wire is parallel to the direction of the magnetic field, there will be no force experienced. Question 3. Remember what I said about questions becoming repetitive? This is another good example of that. So a science technician sets up the apparatus shown below to demonstrate the motor effect. So causing movement using a permanent magnet and an electric current. He uses a powerful permanent magnet. So here's our permanent magnet, north and south. The copper roller is placed across the metal rails. When the switch is closed, the copper roller moves to the right. So it's going to move in this direction. This happens because copper is an electrical conductor, an electrical insulator, or a magnetic material. Well, you know the only magnetic materials in the whole universe are iron, nickel and cobalt, so it can't be that one. And we also know that copper is an excellent conductor, so it can't be this one. So we're going to draw a ring around the correct answer, which is copper is an electrical conductor. And because it conducts electric current, it will generate a magnetic field and then it will be moved along because of the motor effect. Suggest one change the technician can make which will cause the copper roller to move faster. So that's just a question about increasing the force. So just like number 1 and number 2, you could increase the current. One mark, current, that's a T. It's only 1 mark. So either increase the current, but of course you could also write increase magnetic field strength. See how it's the same question over and over. How can we increase the force? So this is just about increasing the force, but look, they've changed it up slightly. Instead of saying how can you increase the force, they've said how can you make the copper roller move faster? But it's the same thing. It's just trying to get you to read the question carefully enough to realise that is what's being asked. Suggest 2 changes the technician can make, each of which will separately cause the copper roller to move to the left. So now we're just reversing the direction of the force, just like in questions 1 and 2. So, just like in those, it's reverse current. Or you could reverse the direction of the magnetic field. So we could reverse the poles of the magnet. Right, the last part of the question, again, isn't really about magnets. This is more a how science works type question. Many electrical appliances, such as vacuum cleaners, drills, CD players, contain electric motors. As more electrical appliances are developed, more electricity needs to be generated. Generating electricity often produces pollutant gases. So we're going to complete the sentence by drawing a ring around the correct line in the box. Generating more electricity to power the increasing number of electrical appliances used raises an ethical issue, an environmental issue, or a political issue. Well, we're told this is about pollutant gases, so the correct answer is an environmental issue. A key mistake children make every year is they don't read the information carefully enough. By telling you generating electricity produces pollutant gases, they are giving you or leading you to an environmental issue. The number of electrical appliances used in the world's richest countries is increasing, yet many people in the world's poorest countries have no access to electricity. What type of issue does this inequality between people in different countries raise? Well, really this is about whether it's appropriate that the rich get richer and the poor remain poor. Would it be ethically better to distribute that wealth in a fairer way? So this is an ethical issue. I know you could also write that this is a political issue. You could write that it is an economic issue. I think it's useful, however, they've given you the words you need in this box. This, I would say, is an ethical issue. Question 4. The questions start to get a little bit more challenging now, but you'll notice that there are still similarities between the questions that appear here and the questions that were appearing at the start. Some people wear magnetic bracelets to relieve pain. Figure 1 shows a magnetic bracelet. There are magnetic poles at both A and B. Part of the magnetic field pattern between A and B is shown. What is the pole at A? What you have to notice is that the magnetic field lines have arrows drawn on them. And really this is a question about the direction of magnetic fields, which you have learnt flow from north to south. So these magnetic field lines at A are moving away from A, so that means A must be a north pole because the magnetic field lines are flowing away. Now this is a trick question because I reckon a lot of people would then write B as the south pole, but you have to look closely. Magnetic field lines are moving away from B as well. Therefore, B must also be a north pole, which means that this bracelet is in fact made of 2 bar magnets. North pole and the south pole will be around here somewhere. North pole and the south pole will be around here somewhere. It's kind of a trick question, and it's about the direction of the magnetic field lines. Over the page, giving another figure. Figure 2 shows 2 of the lines of the magnetic field pattern of a current carrying wire. So we note it is a straight wire and therefore the magnetic field is circular around that wire. And look, it's another question about reversing the current. The direction of the current is reversed. What happens to the direction of the field lines in the magnetic field pattern? Well, they are reversed as well. Then in figure 3, we've got another version of Fleming's left-hand rule. Again, we have to be a little bit careful. So I've got, the thumb is given this time, direction of force. So we've got the second finger is the direction of the current. And the forefinger is the direction of the field. So you only get 2 marks this time because the direction of force is given. Figure 4. We've got another wire inside this time a magnetic field from 2 permanent magnets. Figure 4 shows the direction of the magnetic field between a pair of magnets. So that's that arrow there. So that tells you really this must be a north pole and this must be a south pole because the magnetic field is going that way. And the direction of the current in the wire, which is going upwards. So I've got the direction of the magnetic field and the direction of the current. And the question, in which direction does the force act on the wire? So now we've got to use Fleming's left-hand rule. So my forefinger represents a magnetic field, so that will go across the page in the direction of those arrows there. My second finger has got to line up, which is quite difficult, has got to line up with the current, which is going up the page. So now I've got my forefinger going across the page, and I've got my second finger going up the page, and my thumb is now pointing into the paper or into the page. So the direction of the force on the wire will be into the paper. Now this is tricky because we're drawing these diagrams onto a piece of paper in 2 dimensions, but actually Fleming's left-hand rule works in 3 dimensions. So the wire, in this particular case, is being pushed into the paper. Field, current up the page, and your thumb will be pointing into the paper. Then remember what I said about repetition. There's only so many questions they can ask on this. 3 changes, suggest 3 changes that would, wait for it, decrease the force acting on the wire. So we could decrease the current. We could decrease magnetic field strength. And finally, now this is tricky, this is not repetitive, you could rotate the magnets. So the force will be at its strongest when the wire is at 90 degrees to the direction of the magnetic field. So if you move the magnets around and change this angle, you will reduce the force, decrease the force. So that last one, you could rotate the magnets around, changing the angle between the direction of the current and the direction of the magnetic field. Question 5. Figure 1 shows one way that the motor effect can be demonstrated. So we've got a circuit here. We've got an insulator which doesn't really have any effect other than to stop the copper wire rolling right out of the circuit. You've got your permanent magnet, horseshoe magnet, and copper rails and a copper wire. So it's a bit like the diagram we had earlier. When the switch is closed, the copper wire moves. Fine. So the question: describe how the direction that the copper wire will move can be predicted using Fleming's left-hand rule. So they're not actually asking you to do Fleming's left-hand rule, they're just asking you how it works. So this is a little bit like the fill-in-the-blank questions earlier. So what you'd say is your forefinger and second finger should be at right angles. So forefinger and second finger should be at right angles to each other. And you point your forefinger in the direction of the field. Point your forefinger in the direction of the field. And you point your second finger in the direction of the current. So you point your second finger in the direction of the current. And then your thumb will point in the direction of the movement or force. That's an E. So the thumb will point the direction of movement. And that's it. It's a bit of a weird one, so it doesn't actually ask you to do it. Forefinger and second finger point at right angles. Point the forefinger in the direction of the field, second finger in the direction of the current. Your thumb will point the direction of movement. We've got some more complicated apparatus. Figure 2 shows the apparatus the student used to measure the force acting on a conducting wire in a magnetic field. The wire is clamped to stop it moving. So the wire is not going to move. That means the force will act on the magnet and push it downwards. And then you'll be able to read that off the balance. So at the moment the balance is set to 0, but as soon as you switch the switch on, the magnet will be pushed downwards and you'll get a reading on the balance. So the student set the reading to 0, the student closed the switch and recorded the new balance reading. The student then repeated the procedure 3 more times, and each time the current was kept the same, and these are the 4 readings that they saw on the balance. Estimate the uncertainty in the balance readings taken by the student and show how you estimate the uncertainty. So what you would need to do is calculate a mean, or the mean of the 4 readings. So that's 0.21 plus 0.23 plus 0.25 plus 0.23, all of which is then divided by 4 because there are 4 results. That comes to excuse me, a mean of 0.23. So from 0.23, the furthest above that, the furthest reading above 0.23 is 0.25. So that's plus 0.2. And actually, the furthest below is 0.21, so that's minus 0.2. So we have an uncertainty. I've got that wrong. It's 0.02. We have an uncertainty of 0.02 milligrams, plus or minus 0.02. So 0.23 is the mean, 0.25 is the highest above that, so that's plus 0.02, 0.21 is 0.02 below it, so the uncertainty is plus or minus 0.02. And then a calculation, just like we were doing last lesson. The student changed the current in the wire and recorded the new balance reading. The table shows all of the data recorded by the student. Calculate the length of the wire in the magnetic field. So if we're calculating the length of wire, we're going to need F equals Bill. And we're going to be calculating the length of the wire, which means we need to know the force, magnetic flux density, and the current. I've got the current in the wire is 2.2. I've got magnetic flux density, which is 0.03 Tesla, but I have not got the force. So before we can use F equals Bill, we've got to use the balance reading to calculate the force. Well, the balance reading's in grams, so using C mu, I've got to convert 0.4 grams to 0.0004 kilograms. To divide by 1,000. In order to turn this mass reading into a force, we've got to multiply the mass, so 0.0004, by the gravitational field strength on Earth, which is given in the table, 9.8. So that comes to 0.00392 newtons. Now I've got that, I can use F equals Bill. So we go 0.00392, because that's my force, equals 0.03 Tesla, that's my magnetic flux density, multiplied by the current, which is 2.2, multiplied by the length of wire. Now I would simplify this, 0.03 multiplied by 2.2, giving me 0.066. So then I've got 0.0392 equals 0.066 times L. Then I would rearrange, giving me 0.0392 divided by 0.066 equals L. So I've got 0.0392 divided by 0.066 equals missed a zero out here, look. 0.00. And this gives us 0.059. Golly. So the length of the wire is 0.0 excuse me, 59 meters. And there's 5 marks for that calculation, because you had to calculate the force first, and then you've had to calculate the length of the wire. Question 6, yet another diagram. The diagram shows apparatus set up by a student. So we have our permanent magnet, we have our wire. Again, we're going from the positive long part of the cell around the circuit back to the negative part. The direction of the current will be this way. Actually, it's always worth, if they haven't done it, putting an arrow on. Closing the switch creates a force that acts on the wire XY. So here's our wire XY. Explain why a force acts on the wire XY when the switch is closed. Okay, so when the switch is closed, a current flows through the wire. So you get 1 mark for saying that a current flows through the wire. You'll get a 2nd mark for saying that the wire then creates a magnetic field. As you know, because it's a straight wire, that magnetic field will be circular. So the wire creates a magnetic field, 2nd mark. And finally, the 3rd mark, we can say this magnetic field interacts, useful word. This magnetic field interacts with the permanent magnetic field. So that's permanent magnetic field. So a current flows through the wire. The wire creates a magnetic field, and this magnetic field interacts with the permanent magnetic field. 3 marks, and you got that written in your book somewhere. People often miss these questions because there's not a line to put your answer on, so be careful, make sure you read everything in the exam paper. The force causes the wire XY to move. Draw an arrow on the diagram above to show the direction in which the wire XY will move. So Fleming's left-hand rule. You've got the magnetic field going into the paper. You've got the current coming across from left to right. And so the force will act in an upwards direction. So I've got the magnetic field going north to south into the page. I've got the current coming across X to Y, so from the positive terminal round to the negative terminal. So my thumb is pointing upwards. So on the diagram, we would draw an arrow pointing upwards. State the effect this experiment demonstrates. Well, we're using a magnet and a current to generate movement. So this is the motor effect, because we've got a permanent magnet, a current, and that wire will move. So this is the motor effect. The student replaced the battery with a low frequency alternating current. The student closes the switch. Describe the movement of the wire. Well, if this is an alternating current, then the current along XY will actually go backs and forwards and backs and forwards and backs and forwards and backs and forwards and backs and forwards. So an alternating current reverses the direction of the current. So therefore, the wire will move up and down. You see how this is just another question about how to reverse the direction of the force. So in the easier questions, it will say, what happens if you reverse the direction of the current? You say, well, reverse the direction of the force. Or it might say, how could you reverse the direction of the force? And you'd say, by reversing the current. In this one, it expects you to know what an alternating current is and understand that that will cause the current to go backwards and forwards. So the force will go up and down. So the movement of the wire will be up and down. And part 2 asks you to explain that. Well, because reversing the direction of the current will reverse the direction of the force. Reversing the direction of the current will reverse the direction of the force.